Hello. Hello and welcome to this read through of Postgres documentation. In this video, we will cover up domain types, object identifier types, PG underscore LSN type, and pseudo types. So we will finish the chapter of data types in this video. So if you have not watched my previous video, you can go ahead and watch those videos on the playlist. We have started with some basic queries. And after those basic queries, we are going to go through the most useful parts of the documentation. So after chapter 8, we will cover chapter 9, and then we will cover more chapters which are required for our study of SQL, in particular PostgreSQL. So let's start with domain types. A domain is a user-defined data type that is based on another underlying type. Optionally, it can have constraints that restrict its valid values to a subset of what the underlying type would allow. Otherwise, it behaves like the underlying type. For example, any operator or values that can be applied to the underlying type will work on the domain type. The underlying type can be any built-in or user-defined base type, enum type, array type, composite type, range type, or another domain. For example, we could create a domain over integers that accepts only positive integers. And how we create it? Create domain authent as integer check value greater than 0. And then you can use this domain type authent in a table where you can specify ID as authent and it would accept positive values, but it will not accept negative values. When an operator or function of the underlying type is applied to a domain value, the domain is automatically downcast to the underlying type. Thus, for example, the result of mytable.id minus 1 is considered to be of type integer, not percent. We could write mytable.id minus 1 percent to cast the result back to percent, causing the domain's constraints to be rechecked. In this case, that would result in an error if the expression has been applied to an ID of value 1. Assigning a value of the underlying type to a field or variable of the domain type is allowed without writing an explicit cast, but the domain's constraints will be checked. For additional information, it says create domain. So if we go there, it is here. It is in the reference chapter. So you'll probably never go there. But you can go ahead and see how create domain works. Now we have object identifier types. Object identifiers are used internally by PostgreSQL as primary keys for various system tables. The type OID represents an object identifier. There are also several alias types for OID, each named reg something. Table 8.26 we will see in a minute. The OID type is currently implemented as an unassigned 4-byte integer. Therefore, it is not large enough to provide database OID uniqueness in large databases or even in large individual tables. The OID type itself has few operations beyond comparison. It can be cast to integer, however, and then manipulated using the standard integer operations. You have to be careful about the signed and unsigned confusion if you do this. The OID alias types have no operations of their own except for specialized input and output routines. These routines are able to accept and display symbolic names for system objects rather than the raw numeric value that type OID would use. The alias type allows simplified lookup of OID values for objects. For example, to examine the PG underscore attribute rows related to a table, my table, one would write select star from PG attribute where attribute EL, that is element ID, my table, veg class, rather than select star from PG underscore attribute where attr ELID, attribute element ID, select OID from PG underscore class where rel name is equal to my table. So you would prefer the first query rather than the second query. While that doesn't look all that bad by itself, it is still oversimplified. Far more complicated Sub-select would be needed to select the right OID if there are multiple tables named my table in different schemas. The reg class input converter handles the table lookup according to the schema path setting. And so it does the right thing automatically. Similarly, casting a table's OID to reg class is handy for symbolic display of a numeric ID. So we have several object identifier types. One is OID, then we have reg class, which references PG class. It gives us relation name. And example is PG underscore type. Then we have reg collation, which references PG underscore collation. It gives collection name, collation name, and then we have reg config, which is PG underscore TS underscore config, which gives us text search configuration, reg dictionary, PG underscore TS underscore dict, which is text search dictionary, reg namespace, that is PG underscore namespace, it refers, and it gives us a namespace name, reg opper, reg oppers, oppers, it is PG underscore operator, and it gives operator name and so on. You can go ahead and read the table on your own. So as such, these are not very useful unless you want to know the internals. In day-to-day work, this type won't be actually useful. So while writing normal SQL queries for your web applications or other desktop applications, you wouldn't actually need this. So all of the OID alias types for objects that are grouped by namespace accept schema qualified names and will display schema qualified names on output if the object would not be found in the current search path without being qualified. For example, my schema.myTable is acceptable input for reg class if there is such a table. That value might be output as my schema.myTable or just myTable depending on the current search path. The reg proc and reg opper alias types will only accept input names that are unique, not overloaded, so they are of limited use. For most uses, reg procedure or reg operator are more appropriate. For reg operator, only operators are identified by writing none for the unused operand. The input functions for these types allow white space between tokens and will fold uppercase letters to lowercase, except within double quotes. This is done to make the syntax use similar to the way object names are written in SQL. Conversely, the output functions will use double quotes if needed to make the output to be a valid SQL identifier. For example, the OID of a function named foo with uppercase F taking two integer arguments could be entered as within single quotes space double quotes foo within parentheses int comma integer and then classified with reg procedure. The output would look like foo integer. Both the function name and argument type names could be schema qualified too. Many built-in PostgreSQL functions accept the OID of a table or other kind of database object and for convenience are declared as taking reg class or the appropriate OID alias type. This means you do not have to look up the object's OID by hand, but can just enter its name as a string literal. For example, next val, reg class, function takes a sequence relations OID, so you could call like this, next val full, or next val capital full, or next val full. You can do any of these. We have a note. When you write the argument of such a function as an unadorned literal string, it becomes a constant of type reg class or the appropriate type. Since this is really just an OID, it will track the originally identified object despite later renaming, schema assignment, etc. This early binding behavior is usually desirable for object references with column defaults and views. But sometimes you might want late binding where the object reference is resolved at runtime. To get late binding behavior, force the component to be stored as a text constant instead of reg class. So now foo will be left at runtime. Then to reg class function and that two reg class function and its siblings can also be used to perform runtime lookups. So again, we have to see table 9.16. There are lots of references to chapter 9. Another practical example of reg class is to look up OID of a table listed in the information schema views, which don't supply such OIDs directly. One might, for example, wish to call PG underscore relation underscore size function which requires a table OID. Taking the above rules into account, the correct way to do that is select table underscore schema, comma table underscore name, detail underscore relation underscore size, and then we have port ident, that is identifier, table schema, and port identifier table name as such class. So these are concatenated with dot from information schema dot tables where some condition you can apply. The code identifier function will take care of double coding the identifiers where needed. Is seemingly easier. Select pgm store relation store size table name from information.schema tables where is not recommended because it will fail for tables that are outside your search path or have names that require coding. An additional property of most of the OID alias types is the creation of dependency. If a constant is one of these types appears in a stored expression, such as column default expression or view, it creates a dependency on the reference object. For example, if a column has a default expression next val, MySQL such class, PostgreSQL understand that the default expression depends on the sequence MySQL, so the system will not let the sequence be dropped without first removing the default expression. The alternative of next val MySQL text does not create a dependency. Reg role is an exception to this property. Constants of this type are not allowed in stored expressions. Another identifier type used by the system is XID or transaction abbreviated XACT identifier. This is the data type of the system columns XMIN and XMAX. Transaction identifier 32-bit quantity. In some context, a 64-bit variant XID8 is used. Unlike XID values, XID8 values increase strictly monotonically and cannot be reviewed in the lifetime of a database cluster. So it asks us to look at chapter 67. So if you want to then look up that, and again that is part of the reference. Right. So we come back, we can go ahead and look at those in detail. A third identifier type used by the system is CID or command identifier. This is the data type of the system columns CMIN and CMAX. Command identifiers are also 32-bit quantities. A final identifier type used by the system is TID or tuple identifier, row identifier. This is the data type of the system column CTID. The tuple ID is a pair block number, a tuple index within block. That identifies the physical location of the row within its table. The system columns are further explained in section 5.6. So we'll see 5.6 later on. PG underscore LSN type. The PG underscore LSN data type can be used to store LSN or log sequence number data, which is a pointer to a location in the wall. This type is a representation of xlog, rex, ptr, and an internal system type of PostgreSQL. So it won't be very useful to us unless you want to learn the internals of PostgreSQL. Internally, an LSN is a 64-bit integer representing a byte position in the right-ahead log string. It is printed as two hexadecimal numbers of up to 8 digits each, separated by a slash. For example, 16/B374D848. The PG underscore LSN type supports the standard comparison operators like is equal to and greater than. Two LSNs can be subtracted using minus operator. The result is the number of bytes separating those right-ahead log locations. Also, the number of bytes can be added and subtracted from LSN using the plus PG LSN comma numeric and the minus PG underscore LSN numeric operators respectively. Note that the calculated LSN should be in the range of PG underscore LSN type, that is between 0/0 and 8F. Then we have pseudo types. Okay. Pseudo types you won't encounter in normal SQL. The PostgreSQL type system contains a number of special purpose entries that are collectively called pseudo types. A pseudo type cannot be used as a column data type, but it can be used to declare a function's argument or result type. So in normal SQL, you won't use it, but when you're writing things like stored block or functions, you might use it. Each of the available pseudo types is useful in situations where a function's behavior doesn't correspond to simply taking or returning a value of a specific SQL data type. So we have any pseudo data type, which indicates that a function can accept any input data type. We have any element, which also accepts that the function can take any data type. Any array is any array data type. Any non-array is any non-array data type. Any enum is basically any enum. Any range would be any range. Any range data type. Multi-range, compatible. Compatible means where automatic promotion can be applied. Any compatible array would be similar. Any compatible non-array, any compatible range, any compatible multi-range will all be similar. C string is C style string, that is null terminated string. Internal is server internal data type. Language handler is a procedural language call handler. FDW handler is foreign data wrapper handler. Table underscore AM identifier is table access method handler. So a lot of this won't make sense yet, but we'll see. Once we'll see more and more of documentation, it will make sense. So remember that we can reference serial types in 8.27. Functions coded in C, whether built-in or dynamically loaded, can be declared to accept or return any of these serial types. It is up to this function also to ensure that the function will behave safely when a serial type is used as an argument type. Functions coded in procedural languages can use serial types only as allowed by their implementation languages. At present, most programming languages forbids the use of pseudo type as an argument type and allow only void and record as a result type. Plus trigger or event trigger when the function is used as a trigger or event trigger. Some also support polymorphic functions using the polymorphic pseudo types, which are shown above and discussed in detail in section 36.2.5. The internal pseudo type is used to declare functions that are meant only to be called internally by the database system and not by direct invocation in this SQL query. If a function has at least one internal type argument, then it cannot be called from SQL. To preserve the type safety of this restriction, it is important to follow this coding rule. Do not create any function that is declared to return internal unless it has at least one internal argument. So let's see section 36 point something. So this is extending SQL, and we are not going to study this. This is beyond this code. In this chapter, we will cover, in this section, we will cover triggers, event triggers, rule system, procedural, and PLPG SQL. Nothing beyond that. Maybe we can cover PL underscore Python, but these are quite light, okay, not for basic stuff. So after this, we will cover chapter 9. It is quite big, it will take some time. After chapter 9, I'll cover chapter 4, 5, 6, 7, and 7. Yeah, 4, 5, 6, 7, because those are basics. Okay, so a lot of, in fact, I think before covering chapter 9, we should cover 4, 5, 6, and 7. Okay, so we might cover 4, 5, 6, and 7, and then we can come to chapter 9. And then we can move on. Then we can basically go back to practical SQL because indexes and FTS will be later in the SQL queries. So what we will do is we will cover 4, 5, 6, 7, and 9. And then we will go back to practical SQL querying. And once we are done with basic stuff, we will go ahead and cover chapter 10, 11, 12, 13, possibly 14, 15, and then we will follow this with the PG PLSQL stuff. So I hope that you're enjoying this read through and finding it useful. I thank you for watching the video. So it is not necessary that you wait for video. You can go ahead and read on your own. And if you have any confusion, let me know in the comments and I will try to alleviate the concern which you have with the PostgreSQL documentation. So thanks a lot for watching the video. I'll see you in the next one tomorrow. Till then, enjoy.